5 minutes avant. Merci. Is it okay? Okay, good morning. I cannot start this talk without evoking the memory of Osman. So it was is it okay? Yes, is it okay? Okay. So I said that it was just 2 or 3 years ago when Lot organized his DIMCO meeting that Osman was in the other room, and as usually we discussed a lot about our talks, other talks, and he was an outstanding scientist and a friend for so many. And of course, as many people, I miss him a lot. So I will talk about our theoretical studies on electron molecular cation at low energy. And more specifically, it is about these reactions, dissociative recombination, called also molecular assisted recombination, raw vibrational excitation and de-excitation, and dissociative excitation, also called molecular assisted dissociation. There are many authors because we attacked many molecular systems, and these are people which worked especially on the collisional part of our research, but we rely strongly on people working on theoretical spectroscopy, namely producing potential energy curves and couplings between the different molecular states, and they are outlined in red. So there are people from Le Havre, or who spent some time in Le Havre, and other people in Hungary. Zsolt is one of the main contributors. Of course, UK, United States, India, and so on. And of course, as I am associated to Laboratoire Nqdt, I benefit of the collaboration of Olivier. So these processes, which are competitive, occur in many media, in natural media like interstellar molecular clouds and planetary atmospheres, different, as I said, natural phenomena, but also in the plasmas occurring at the entry of the spacecraft in planetary atmospheres, at the walls of the fusion reactors. So it's a very important issue for the loss of electrons and different thermal exchanges at the walls of ITER, for example. And also in many plasmas involved in some industrial processes, especially treating of surfaces, coating, and so on. I should also mention that these processes are measured. So the cross-section, the rate coefficients are measured in storage rings. This is a storage ring which does not exist anymore. It is a magnetic one, but many results I will show you come from this kind of measurements. And now we face the generation of new storage rings of electrostatic nature, let's say. And once again, this is the storage ring of Heidelberg, but there are others in Sweden, in Japan, and in Denmark. So you will not be surprised if I say that the various mechanisms which drive the dynamics of these systems depend on energy. And these systems will be, for me, much simpler than those we have seen this morning before. Diatomic molecules, triatomic molecules. Within a collaboration with Slava Kokulin, we attacked also larger molecules, and the larger one was a 7-atom molecule, which was of interest for astrochemistry, but I will restrict to more simple systems. So in order to illustrate some general feature, I will start with an example for the most simple molecular ions, H2 plus and its isotopes. And there is a typical behavior of the recombination, if you take one of the processes enumerated, which was put in evidence by all the 3 European storage rings many years ago. And I think there is much physics in this picture. What you can see here are 3 cross sections. They are multiplied by 10, one relative to the other, because otherwise they are quite similar and we cannot distinguish very well the features. At very low energies, you have very often a 1/E behavior of the cross section. There are some notable exceptions. I will talk of one of them. At moderate energies, you have narrow resonances, Fano type resonances. They are not quite Fano because they are quite intricate, but this is a very interesting region. And at higher energies, you have very broad resonances. Now, of course, this is specific for H2 plus collision with electrons, but many of these features repeat at other energies for other systems. Another very interesting example is CH plus. At the end of the 90s, we have seen some resonances which were between these 2 types I illustrated before, which were not easy to explain at that time. And I will talk about this kind of resonances. So I will just illustrate some basic features for within the multi-channel quantum defect theory approach. And generally speaking, what is very interesting for this kind of processes, and here I illustrate it with dissociative recombination, is the quantum interferences between 2 paths, one going directly to a dissociative state, and the other going via some bound Rydberg states, which are pre-dissociated by the dissociative state labeled here by these 2 stars. And this interference will generate these very pronounced resonances, an infinite number of resonances, which are related to this, which are described by these Fano profiles. And of course, it is of huge interest to discuss about the molecular structure part, especially in the context of this meeting devoted to how machine learning can help the quantum dynamics calculation. This is a typical landscape of states, and to compute these states, of course, to compute the electronic states of the target, it can be done by MolPro. I don't say it's very easy always, but it is more or less standard. But if we talk about the neutral states, and this is within this symmetry for H2 system, it is not easy to do it because we face Feshbach resonances, and some groups devoted their work to the computation of these states. More specific, so these 2 curves, the black one and the orange one, are the ion electronic states, the target electronic states. Anyway, the relevant ones for low energies. What you see here, the colored states, continuum colored states, are the valence dissociative states, which are the Feshbach resonances. You also have to consider, especially at low energies, and this is of huge interest for astrochemistry and cold plasmas, the Rydberg bound superexcited states, the Rydberg resonances. And all this, you may be surprised by these crossings within the same symmetry, but all this happens in a quasi-diabatic representation, which we need for different reasons I can explain, and which makes the determination of this especially Feshbach resonance, is a difficult task. And this process is also beyond Born-Oppenheimer context. So we have a superposition of states, of all these states, and practically, if you look here, you may understand that you have an infinity of Rydberg states which are involved. And finally, this quasi-diabatic representation is compatible with the fact that what you have in this kind of system, like H2NOCH and others, not in all of them, but in many of them, what is called the Rydberg valence coupling, which is related, if you work in adiabatic representation, to the avoided process. So here are some typical other molecular data. So I have shown you some typical states involved, but here are some couplings, electronic couplings between, let's say, the Rydberg states and the Feshbach resonances, or between electron plus target states and the dissociative states. And here are some quantum defects. All these ingredients are needed for the dynamic calculations. Some words about the theory, the method we use, and I will then, the rest of the time is examples and relevant results. So we work with a version of the multi-channel quantum defect theory, which was funded by Seaton for the atoms, and which goes far beyond this simple formula, because the quantum defect makes the link between the discrete part of the spectrum and the continuum, and all the theory is much more sophisticated than using just this continuity. It was extended to molecules by Fano, Jungen, Christian Jungen, which worked here in Orsay and it's still working. Chris Green, Anik, which was working on Orsay, Takagi in Japan. And I will just illustrate quickly the main steps in the Nqdt method we use. Of course, we rely on the couplings between the states. And very quickly, this is the electronic coupling, which is coming from the pre-dissociation widths of the Feshbach resonances. And here are the wave functions of these resonances, these resonance states, and the wave function of the target ion on different rho vibrational states. Now, once we build what is called interaction matrix, relying on these integrated couplings, we construct the reaction matrix. This is a matrix operation. And then we diagonalize the K matrix. And these quantum eigenvector and eigenvalues are involved in this formula of the frame transformation to the external region as any collision process. And you have some angular factors and which are important if we take into account the rotational structure of the molecules, which is not always necessary, but at very low energies, it's crucial. And then, as I said, the quantum defect is involved in this frame transformation. And these eigenvalues are also involved in these terms. And having this frame transformation matrices, we built what is called the generalized scattering matrix X, which is particular because it involves not only open channels, but also closed channels. So we have a block structure of this matrix, and eventually we compute the physical scattering matrix, which contains this resonant term here, and it is at the origin of the very rich resonance structure you have seen before. And at the end, we introduce the matrix elements of this physical scattering matrix into the formula of the dissociative recombination and vibrational transition, excitation or de-excitation. Now, going back to this idea, I will illustrate it going progressively from low energy to high energy. At very low energies, taking again for the beginning the H2 plus isotopologues as examples, we will see some typical features. But first of all, why is this so important? Not only from a heuristic point of view, but also because astrochemists rely on data, on many data, but also on the data of collisions between electron and molecular ions, for example, in the kinetics of the early universe. And what is the region I'm talking about? This one of about 1 electron volt, between 0 and 1 electron volt. I'm talking about the energy of the incident electron. These are the features you have to recognize in the theoretical and experimental cross sections. And we studied this for HD plus at the beginning, then H2 plus, and very recently for D2 plus. And I will give you some examples from here. This is a typical result, the black one, dominated by this resonance. This corresponds to the dissociative recombination of D2 plus in its completely ground state. And this is, of course, scaled, the Maxwell rate coefficient. Very often, this is what is needed from astrophysics, although the cross sections are useful when you want to do more, when we want to take into account the non-equilibrium aspect of this media. And here is the spread of the rate coefficient, Maxwell rate coefficients for the same process, dissociative recombination. You may see that you have a spread on more than 2 orders of magnitude. And that's the reason a very accurate evaluation of these cross-sectional rates is needed, including rotational effects. Now, we are about to spend much time to compute such rate coefficients for practically all the isotopologues of H2 plus. Here are some examples of H2 plus. Astrochemists need for their model for the Earth universe some hundreds, to have data on some hundreds of states, the lowest 300 states, for example, for H2 plus, HD plus, in order to make a state-to-state kinetic model. And we are about to produce this kind of data. Here you have an example of what happens, what rotational excitation and in the same time with vibrational de-excitation you may have, and what are the Maxwell rate coefficient for different rotational levels corresponding to the first excited, the lowest excited vibrational level, and to the second one. So the agreement with experiment is quite good when you are talking about rate coefficients. You may focus on this dashed curve, which is the experiment, and the green one, which are our calculations, corresponding to a rotational average of 300 Kelvin. Of course, we have tried different temperatures because nobody knows exactly in the storage ring what is the temperature, but you can look to this like the fact that the correspondence between theory and experiment works like a thermometer for the rotational temperature. And now we agree more or less that the temperature is around 300 Kelvin, was around 300 Kelvin. And you see that the agreement is not bad at all at very low energies, and a little bit less good, but quite satisfactory at higher temperatures. If you look to the cross sections, they are convoluted with apparatus function of these storage rings. The results are not so bad, but you see that this zoom on the reality shows that there are serious discrepancies in some regions. And this should be a state-to-state landscape, and it's encouraging, but it's far from being perfect. So there is much work to do on that. Now, the idea is, of course, we have to be more accurate, especially because now we have a new generation of storage rings in which this problem of rotational distribution of the target is no more actual. This CSR storage ring, cryogenic storage ring, is able to resolve for rotational levels 0 and 1 or even 0. So the focus is more serious on the accuracy of the theoretical result. This is an example on CH+. This is a distribution of CH+ dissociative recombination Maxwell rates. You see that it's much less spread than for H2+ and its isotopes. So let's climb a little bit to moderately low energy or moderately high energy. So we go from this region to this one. So we climb to typically 3 electron volt. This is valid for hydrogen, but not far from other systems. And rotation can be neglected, especially for if we want to help cold plasma modelers, because they are at higher temperatures. We can speak in this kind of plasma of temperatures between, let's say, 300 and 40,000 Kelvin, as long as the molecules exist. So this is a typical landscape of cross sections for different vibrational states of the target for H2+, for all the processes, dissociative recombination, the vibrational excitation, the vibrational de-excitation. And this is another result for argon H+, so I will just show you some examples. The main features have been already illustrated. You see here that the dependence on the vibrational excitation of the target is very, very strong. And you also seen that this is an untypical behavior, because the cross section is not going like 1 over energy, but it's 0 at low energies, contrary to what happened to hydrogen and to most of the systems we studied. And the experiment shows that very clearly. This is an experiment performed in the Astrid storage ring. And actually the explanation is quite simple. Unlike to hydrogen, when the lowest dissociative state is open, you may see that the asymptotic limit of this state is below the lowest vibrational state of H2+. The lowest vibrational state of argon H+ is much below to this asymptotic limit. So this is quite, if you can compute all this curve, you understand quickly what happens. Now, if you want to make quantitative evaluations, you see here that we did it and we have a rather good agreement with these experimental results. Now, a very interesting phenomenon related to this figure I already showed to you is this resonances, which nowadays we know can be attributed to core excited Rydberg resonance. What it is about? Very quickly, an explanation. This is the electronic ground state of CH+. So this is where the target is on one of these vibration levels. Let's suppose it's on its ground vibration level. This is the main dissociative state, the double pi CH state. And the problem is that this is not, as I said, this is not the only relevant state of the target. You have second state, which is very close to this one, and not only the fact that it is closed matters, but also the fact that it is bound, unlike for hydrogen. And that means it supports Rydberg series here. And here is a second excited state. So all this must complicate much the landscape for the cross section. And indeed, we can follow the evolution of the accuracy of our method, looking to the comparison with experiment, as long as we add all these cores as ionic cores. So if we have the direct process with only one ionic core, this is the cross section. So clearly disagreement with experiment. If you add the indirect process, that means the quantum interferences, then you have another landscape, but it doesn't change too much the average effect. This is what happens when you allow for a second core. Then all the Rydberg states pertaining to this core will induce these features. And we are lucky because some of these high resonances occur more or less in the same place when the experimental resonances occur. Then we had the third core, and this feature is more dominate. It's more important, more visible, and of course you cannot stop here. You have to convolute, and this is the final result, working in the second order of our calculations with all the three cores included and taking into account the indirect process. So you may say it's not a brilliant agreement, and you're right. However, this is no more a logarithmic scale, but a linear scale, and we reproduce more or less these all these resonances put in evidence by the experiment, even if the position is not always the best one. There are new calculations nowadays on CH+ by the group of Slava Kokulin, and there is some progress in the agreement between theory and experiment. Not to speak about the fact that there are new experiments which contradict the old ones, and so it's a permanent challenge to have this dialogue between experiment and theory. Now I will quickly go to other systems. Another system subject to core excited effects is nitrogen 2+, relevant for atmospheric entries in the Titan and Triton atmospheres and in some natural phenomenon on Earth. So also SH+, which was discovered recently, you have to see here a comparison theory experiment, which is not bad, but which is rather good for some region, but fails at very low energies. So for the astrochemists, we have to work furthermore to understand this agreement. CO+ for comets, for the atmosphere of Mars. This is the vibrational dependence of the dissociative recombination. And the processes I have told you about at the wall of the fusion reactors, especially beryllium H+, which comes from the erosion of these walls, which are, as you probably know, built nowadays from beryllium and not from carbon. And we scanned all the three isotopes of beryllium H+. And I want only to show you a very nice feature concerning the isotopic effects. If you represent for the three isotopes the rate coefficients for different temperatures, but not in function of the vibrational level, but of the energy of the vibrational level, you have, from the plasma physicist point of view, practically the same behavior. And this is very useful for modelers of the collisional radiative kinetics in cold plasmas. And the last example of this kind is from a process called plasma immersion ion implantation. We computed the same rate coefficients, same time of rate coefficients for collision between electron and BF+. Now, for some years, we collaborate with the group of Slava Kokulin and Mehdi Ayus, who is here. Mehdi is here in Central Supélec, in order to look to polyatomic systems. And the first trial was boron fluor 2+. And it happens that this one is much more important than the BF+. So the complex system gives rates which are stronger than that of the diatomic system. You may compare the continuum line to the dashed one for the dissociative recombination and vibrational excitation. And at high energy, to finish this analyze, what is high energy? This is the field of the high energy. So we are above the asymptotic limit of the excited state, excited electronic state of the target. Now you have other phenomena which add to the previous one. First of all, the Rydberg resonances disappear, and you have the vibrational continuum, and you have also an infinite series of dissociative states. So we obtain nice results for beryllium H plus at high energy, argon H plus. And for the near future, of course, we have to continue of this. There is a very breakthrough paper of Chris Green and his co-workers, which improve tremendously the agreement theory experiment within Nqdt, and we want to do the same for, this was for helium H plus, we want to do something similar for H2 plus. Probably to illustrate very recent result on NS plus, which was discovered 3 years ago. We prepare also dynamical calculation and new efforts for CF plus and for the polyatomic systems, new calculations of N2H plus, which improve significantly the agreement theory experiment for very low energy, that is for the field of interest for astrochemistry. So concerning the machine learning, is it important for us? I was not a good pupil, so I didn't come to the previous days of this meeting. However, I may say, maybe it's naive, but one of the problems we have is that all these molecular input data are determined on the very limited range of internuclear distances. For example, you may see here, for example, these couplings die suddenly here in our calculations, but this is not true. They should continue. But how they would continue, this is a big question. How sensitive are our calculations to this? So this is, I think that machine learning may help us if these calculations could be related to this technique in order to try different versions of these extrapolations, which could be, I'm almost certain they are important for the final result and the values we provide to models. And with that, I thank you for your attention.
So let's see if it works. Yes, thank you so much for this review. I have, because you are addressing this last question of machine learning, so I have to admit that I'm puzzled as well by the possibility to use it or not. But there's something that I have in mind, which maybe also may have some connection with the see that you have shown and the theory. As you said, you that those discrepancies are not the same depending on the energy zone that you have. The issues are not probably the same. Yes. So I think just so this is just a general statement of what I say. What I'm saying so strongly depends on the electron calculation, which are not precise. At low energy, would be do you change something? And what where this discrepancy comes from?
We do this kind of numerical experiments indeed, but actually the process is very sensitive. First of all, it is the process or the cross section is very sensitive to the input molecular data, as you said. We did move in some band of energy, or to be more precise, some band of quantum defect, some band of couplings. But actually, it is strongly nonlinear. And unfortunately, you cannot control even this uncertainty in a simple way. So one source of uncertainty is the quality of the molecular structure data, more precisely, in general, R matrix calculations. On the other hand, we are aware of the fact that our method has some intrinsic errors. For example, as I said very quickly about what Chris Green achieved, taking into account the energy dependence of the quantum defect. In our theory, the quantum defect is constant. It doesn't depend on the energy. And this is certainly a source of error. So we think we know what are, and there are other approximations that it's no time to talk about. So there are sources of errors which we identified. I should say that the molecular structure data are the most important, but there are some defaults in our method. And the last word is that the use now, the method which is used by Slava, and we try to use it together, makes a big step forward because it avoids to compute prior to the dynamics the potential energy curves and the couplings using the quantum Mole package of codes of Jonathan Tennyson, and they provide directly the K matrix without spending time and energy with the potential energy curves and so on. And this has enormous advantage, less precise, but maybe this is the way to avoid a lot of complication, because all is contained in the K matrix, in the electronic K matrix. And I believe this is one of the paths, not the only one.
Okay, thank you very much. I think we'll stop here and then you can keep discussing during the breaks. Let's thank Ioan again and all the speakers from this session. And is there any announcement? No? So back here at 2, and you know where the lunch break is, it's where the coffee break was.